Welcome to Computer Science 305, Programming Languages, and today we'll be talking about concurrency. And this is, I think, the last lecture that I'll actually be posting online. Anyway, concurrency is pretty much one of the most important topics, I think, of this entire class, in that it's one of the most relevant to what's going on in the field today. Anyway, so we'll get started. Basically, concurrency can occur at essentially 4 different levels. 3 of these, or 2 of these, I would say we actually can really be concerned about. But in essence, there's the machine instruction level, which is down in the hardware when an instruction shifts into, or when the actual computer system is interpreting the instructions. What can happen is it can reorder your instructions to improve efficiency and also to allow for multiple instructions to actually occur at one time, right? So it provides concurrency automatically through pipelining and super pipelining, along with some other techniques that are used at the hardware level. On the other end of this spectrum is what we call program level concurrency, where we have more than one program executing on the system, and this is at the operating system level, right? The system loader loads up the programs, and then there's a scheduler that assigns these programs to different processors or provides different time slices on the same processor. And so both of these are really outside of our control, right? As a programmer, we can't make the decisions for the scheduler, nor can we do anything about how the hardware is going to handle this. But what we can do is we can utilize the frameworks and API capabilities and language techniques that are available to us at the high-level language statement level, right? So we actually can utilize different aspects inside of our language to start and create new concurrent objects, as well as at the unit level where we actually define these different constructs to allow us to have concurrency. And so this is what we're going to be talking about in this section of the class, right? So we have to go all the way back to the 1950s, really get us a handle on this, right? Because when we start thinking about concurrency, one of the major things is we have to be connected to the hardware. We have to understand how that actually, not at the deep level, but at least at an abstract level, how this is going to work with the program that we have, right? Or with the language that we have. And so we have to go back and think about, well, when did we really start gaining this notion of having multi-processors? Well, it was back in the 1950s when we shifted from just having a single general-purpose CPU to having not only that, but also an I/O operations processor, right? Because I/O operations were always blocking up the ability for programs to finish because they're sitting there waiting to write to files or later on to the network. And so in order to prevent any further processing from happening when that was occurring, we decided to have a special input-output processor. So we could have multiple programs running. If one gets blocked up by the I/O, the operating system will move that onto this, or needs to use I/O, it moves that program over to the I/O processor, lets it go do that, and then that opens up a path for some other program to continue working. And then when the I/O operation finishes, it will eventually shift back into being scheduled onto the main processor. Now, that was all great. But it wasn't until and from that we said, oh, well, maybe we could have more than one processor, right? So then we started building systems that had multiple complete processors available, right? Now we can have true program level concurrency, right? The operating system can schedule programs to to different processors, allowing them to just complete their execution by themselves. All right, that's great. Now, from that, in the mid 60s, they started developing multiple partial processors, right? So now you have individual sub-processors within a single processor that can then allow us to have what we'll call instruction level concurrency, right? So you can have multiple instructions operating at the same time. And then, of course, you have to have the capability to reorder correctly such that the expected outcome is correct, which they have all sorts of different techniques for. But that kind of got us, and now where we are is we have something similar. We have a single processor with multiple full processors, multiple complete processors inside of it, right? So that would be like the Intel, the current Intel architecture has typically on a average laptop will have anywhere from 2 to 4 cores, and then they have hyper-threading in there, which allows you to work on both the up and down cycle. You can get systems that have 8, 16, 12, 6, 64 cores if you pay for it. You can have multiple processors with multiple cores. So essentially, we've gotten all sorts of new power, right? But that's following Moore's law, right? The number of semiconductors that we can fit in a single silicon wafer is essentially doubles every 18 months or so. Well, that's awesome, except for it used to be that we got faster and faster, but it got to a point where we can no longer effectively cool the faster and faster we made these chips. So we decided what we should do instead is just add more and more cores, so our computational power has increased, but the speed has not. Anyhow, for over the years, right, before we had this multiple full processors on a single within a processor, we were envisioning a way to think about this, and we created these abstract notions, and so or classifications for these different types of machines. And so the two most common ones that we'll be dealing with, there are several others, but the ones that we'll be focusing on are SIMD and MIMD. So SIMD, or single instruction multiple data machines, basically are saying that for at any one time we can have a single instruction processing, but that single instruction can handle multiple data. We'll say multiple data inputs, and be able to handle those correctly, right? So we have multiple potential data movements that are going on at any one time, so we can read from multiple places, but we only have one instruction that we can actually execute on the other at one exact point in time. On the other hand, we have multiple instruction, multiple data machines, which are more like what we have right now, which is we have multiple processor capabilities, so we can have multiple instructions executing at a single point in time that can then handle multiple reads on data. So, which is excellent, right? And so what we'll be focusing on, so most of the stuff that you've talked about in all of your other classes prior to this has been dealing with what we call the multiple data, the SIMD machine, right? Where you think of it as you have a single instruction executing at one time, and then we have the potential to access all of memory whenever we need to. Well, that's we're going to shift away from that and think about what if we had multiple instructions executing at the same time. So this shifts us into, well, we need to start thinking about the categories of the type of concurrency, right? So I do want to step aside for just 1 second here. Well, actually, this is exactly where I want to be. So we have, well, a lot of people will argue that there's a difference between parallel processing and concurrency. Concurrency says at the same time we can have two things happening, or two or more things happening at once. Parallelism says we've designed it such that it can operate more than one thing can happen. It can work more than one thing can work together, but not necessarily at the same time. So the difference. So when we think in this lecture, when we're talking about that, that's essentially the difference between physical concurrency and logical concurrency. I would argue that physical concurrency is true concurrency and logical concurrency is parallelism. So now if we think about this, physical concurrency is telling us that we literally have multiple independent processors, which then give us the capability to have multiple threads of control within a single program. On the other hand, we have logical concurrency, or what I would call parallel processing, which is the appearance of physical concurrency presented via time sharing of a single processor. So it's not true concurrency, but things are apparently executing in parallel, right? They're not all executing at once, but it's not that I only execute one thing and then when that's done, I execute something else. They're all executing in parallel, but they're not executing concurrently. So this kind of is captured by software can be designed as if there were multiple threads, of control, even though there are not. On the other hand, we also have coroutines, which is quasi-concurrency, in that we have a single thread of control that swaps between a bunch of different routines that are designed such that they work together and in parallel. Now that we have that kind of worked out, we have to understand what do we mean by a thread of control. So let's envision, I wish I had a diagram. I don't have one on me right now. But envision a program executing from when you start it to when it ends over time as a series of statements that are occurring. This could be the construction of an object, calling a method on that object. What happens, and then shifts us into the method itself, and we execute each one of those. Now we're thinking of this serially, right? As if there's only a single thread and it executes one statement at a time and jumps around, but we're only thinking about those statements as they execute. So that sequence, and we'll call each one of those statements, right, or instructions, as a node in a graph, right, and it's just a straight line. Now we think of that as the thread, that the links connecting each of those is the thread of control, right? And so if we are in a multi-processing situation or a concurrent situation, we can actually have where when we start the program, that turns on the main, think of this in Java, right? So you have your main method, and when that executes, that sets up the main thread, right? This is the thing that we typically follow. It's where all of the code that we write typically executes. But there are other threads that are in parallel to that, right, are concurrently executing. One is the garbage collector thread, and the other would be the Abstract Winning Toolkit's event bus thread. So these things execute in parallel, but the main thread of control is what we have. We can actually program and can take control of ourselves, right? That's where our program logic lies. And so if we create new threads, they branch off of that, and then they can create their own. They're also parallel executions. But we have to understand that if that main thread stops, everything else stops at the same time. So we have to keep that in mind. But anyway, a thread of control is simply just the sequence of program points or statements being executed as the control flows through the program. So just think about that. So the motivation for using concurrency, so now that we know what thread of control is, we understand the different types of concurrency, how this kind of came to be. So now we're asking ourselves, why is it that we actually need to do this? What does it matter? Well, I alluded to Moore's Law issues, but we also note that multiprocessor capabilities has finally become extremely widespread. Like, I remember back in 2005, 2004, etc., where we were actually it's 2003 when I got my first multi-core machine, and it was like amazing that we had this, right? But it's rare to find programs that really effectively utilize that capability beyond just the operating system assigning programs to different processors. So that's awesome and everything, but it's not the best that it could possibly be. And furthermore, but given that it's become so pervasive, and distributed computing and the ability to use like single board computers, and that you can integrate together into a small cluster and things like that, this all becomes gives you this vast capability to utilize this computational power that just didn't exist back 10 years ago, So if we have that, this is the motivation, but also because we have so much more data now that we have to process. We have so many more. The problems that we're trying to solve today are not only more challenging, but also more data intensive and more computationally intensive. And so developing programs in a way that takes advantage of the underlying hardware is a necessity in today's world. So, and furthermore, even if you do stumble across a system that has only a single processor, you can still develop your program in a way that uses concurrent execution, and it will more than likely be faster than if you designed it in a sequential way. So bear that in mind. Furthermore, right, just doing all this involves a completely different way of designing software to be useful, right? We have to think about a significant number of things really involve, real world situations involve the use of concurrency. And if you don't do it, you are going to, seriously lose a lot of computational, you throw computational power just in the trash. And that's not what we want to do. Beyond a simple one system program that you're writing, the same techniques that you learn when you learn about concurrency, learn about programming in this way, and thinking in this way, apply now when we start integrating multiple machines together, working across a network, and now we're getting into the world of distributed computing and cloud, based systems. So thinking in that way, now we have this even more difficult problems to solve, but really basically are the same problems, just without the extreme speed of a memory bus. We now instead have a network that we have to deal with. So now we will shift away from thinking about those problems into the world that we actually care about, which is this sub-program level concurrency, right? If program level concurrency is at the operating system assigning different applications to different processors, sub-program level concurrency is then concurrency within a single program and how it's going to handle constructing new tasks or threads or processes within its own address space that it's been allocated by the operating system. And so that gets us to this first bullet point here, right? So we have to ask ourselves, well, what are these things that we normally think of? What are threads, or some places call them tasks, or other languages call them a process? What is really the difference between this? Well, in the world of subprogram concurrency, they're all the same thing. But if you are looking at a more operating system level construct, a thread is what we'll call, shortly here, a lightweight process, and a process, as it's typically called, is a heavyweight process. And we'll talk about what that means in a minute here. But we have to think about how these things differ from what we normally think of in a program, right? So a subprogram is a part of any one full program, right? It could be, in Java, it could be like what we'll call a class. In C#, we can get down to the method level. In other languages, we call them subroutines. There's a lot of different names for these things, but essentially, these are just parts of a program that we can then execute. While tasks differ from these things in that they may be implicitly started. They have the ability to when a program unit starts the execution of a task, that program unit itself doesn't suspend, right? So if I execute a different program unit from another one, it suspends the processing of the calling program unit, right? So we have to think about that, and until the other one is done, right? And then we have to think about this as methods, right? If I call a method from one method, the calling method suspends operation until the method it calls returns, right? And it returns directly back to that same calling method. Well, when we are dealing with tasks or threads, that's not necessarily true. It probably doesn't go back to whoever forked that process unless we explicitly state that will happen. And furthermore, the main thread that we or the thread that we of control that we started from, we started the other one from, doesn't suspend. It probably will continue going, continue its execution as if nothing happened. So we have to think about that when we start thinking about how these programs will work, right? And finally, we need to understand that one of the goals of this is typically to make it so that all these different tasks or threads are working together to solve some major problem, right? And then that becomes, well, how do we make that happen? Well, we'll talk about that. So continuing with what I was talking about with different categories of tasks, right? The nomenclature of process versus task or process versus thread. I like the fact that they're using the word task here, mainly because it kind of subsumes both thread and process, where thread and process are kind of specific to different domains. But a heavyweight task is one in which it constructs its own address space in memory that is disjoint, completely separate from whatever spawned that process, right? Which we actually call is a term called forking. We fork a process, and so if it's a heavyweight task, that will have its own memory space, which then entails that the construction of that thing will take far more time than the other one, which is a lightweight task, which does not require a new address space. It will operate within the same address space of that which forked it. And so, which also is more efficient memory-wise, but leads to a whole slew of problems, because when you're disjoint, right, you have disjoint memory, and that means there's no real way for two heavyweight tasks, which are typically called processes in the operating system space. These things are incapable of communicating with each other, and thus they have no effect on one another. On the other hand, lightweight tasks, because they're in the same memory space, can then communicate directly with each other and also have a problem of being affected by one another. And so that leads us to all sorts of problems. So for pretty much the duration of this, we'll be talking about lightweight tasks, and because we're talking about in the shared memory space. And so, and I'll probably mostly refer to those as threads, although you'll see task everywhere here. So that leads us to, when we're dealing with this sort of lightweight thread problem with this potential for them not being disjoint and they can communicate with one another, that means we then have to start dealing with the concept of synchronization, right? We can't have, and we'll talk about why we need that in a minute here, but synchronization is simply just a mechanism controlling the order in which these tasks perform different operations or execute, right? And there's two different major kinds of synchronization. The synchronization we need to be concerned with: cooperation and competition-based synchronization. And so, in order to make this happen, in order to make synchronization occur, tasks must communicate with each other. And the three major ways that we have for this to occur is through the use of shared non-local variables, right? So fields of objects or global variables in different languages. Through parameters that are, parameters to classes, parameters to the tasks that allow us to communicate. And finally, through message passing or method calls, as we normally think of them in object-oriented systems. So these types of synchronization, right? We have those three methods by which we can communicate to make synchronization occur, but the two different kinds are essentially defined here. We have in cooperation synchronization, we essentially have this interdependency between two tasks, right? We have task A and task B. And the problem is that task B it's currently doing something, and whatever that is going to cause task A to wait because it's depending on the current processing that task B is doing. And it will not continue, task A will not continue until task B has finished, right? Once task B finishes, task A can continue. And this is what we call the producer-consumer problem, right? We have some producer, task B, and some consumer, task A. And that implies there's a relationship. A consumes what B produces. On the other hand, we have this competition-based synchronization where we have two or more tasks and some resource. And this resource, only one thing can use it at a time, cannot be simultaneously used. We can think of that as like maybe a file, a locked file, or a shared counter, or like maybe a network stream or something like that. And so we have to ensure that only one resource accesses at any one time. And this is called mutually exclusive access. And that's how we're going to provide this competition, right? So these things, and what will happen is when one thing is using it, and until it's done using it, everything else that needs it will wait. So we'll discuss how we actually provide both of these types of synchronization a little bit later. But understanding this competition synchronization, why we really need it, right? So let's say we have some resource total. Total is just some value. Well, if we were to write this in a sequential way, as we normally think of it, as we have this value total, it starts at 3. And what we did was we wrote the two lines, total equals total plus 1. So that would make total now equal to 4 once that executes. And then we have the next line, which is total equals 2 times total. And that will make, that will then say total, once that executes, will be 8, right? That's the new value of total. So in a sequential way, this makes sense. We just look at it, we think about it, and we can see, the correct answer would be 8. Unfortunately, though, if we did this with the two tasks as shown there, task A and B, where task A handles the addition portion and task B the multiplication, if we don't do this correctly, what will end up happening is we have essentially 4 possible different results that can occur. And we're showing one here, where if over time, as we see here, we have task A and B. If task A reads, then task B reads, then task A adds 1, and then task B multiplies by 2, and then task A stores total, right? So you got to think about this. It's not updating anything as it goes along. It's not updating until we do store, right? So we read, we have this local variable value that we have, which is 3. We add 1 to that local value, and then we're going to write it to the holder in memory total, right? And then task B does something similar, except for here it has its local value. Now it reads in, it's 3, right? Because nothing has changed. And then it says, I'm going to multiply that by 2. So it has its local value now, which is 6. And then now it's going to store that, right? But that storage happened after task A's store. So it's going to overwrite that. And now total appears to be 6, which is still wrong, right? The first one was wrong. Well, would have been right, except for we should have been reading after that happened. And this gets us into this concept called atomicity, right? So we want an atomic operation. So an atomic operation basically says that at any one time, if an atomic read would be, when I go to read this, and I am the only reader right now that looks at this, and I do the, and then when I'm done, anyone else can read it as well. So we want an atomic operation to be essentially an order 1 operation. So order 1 operations by definition are atomic. Anything else that's not order 1, which in this case would be the read, add 1, update, right? We want that to be an atomic operation. But since it's actually 3 operations, we want to redefine that such that task A can go and read total, add 1 to it, and then update total without anyone else being able to read total right? While that's happening, we don't want anyone else doing anything to total while we do this. Same can be said for task B, right? Task B wants to read total, multiply it by 2, and store that new value to total. But we don't want anyone else coming in the middle of that, reading the incorrect value until we're done. So we have to have some way to lock total down while we do this. And so that's kind of what we're going to get into. Well, the whole way of this is all being done, at the program level at least, is that we have this synchronizing mechanism which delays task execution, right? And that's done at the program level with the scheduler. Well, we have to come up with some other way to do it at the subprogram level, right? And in order to ensure that task execution across processors is correct according to whatever our constraints are. In this case, we need what we call linearizability, or sequential, equivalent to sequential ordering. In order to understand this, right, so just bear all that in mind as we go through this. We have to think about our task or our thread, right, and that it has different states it can be in at any one time, right? So when we first construct a thread, it starts out in a new state, right? It's been created, but maybe it's not ready to go. It has to initialize first. Once it's initialized, it enters the the ready state, and the ready state says, "Well, I'm ready to run and process, but I can't do that until you assign me a processor." So the scheduler goes, picks a processor for this, and then assigns this task to a processor, and then the task enters the running state. Now, once it's in the running state, it can go and it will go along, do its computation as much as it possibly can until it hits a point where it can no longer process. Now, it could be blocked. We could force it into a state called sleeping. We can let it yield right when it's waiting on, but essentially it's waiting for some event to occur. All these are blocked state, right? So then it leaves the running state, hits blocked, and it sits there and waits, right? It could maybe it's waiting for a certain amount of time to elapse, an event to occur, something to happen. And once that occurs, it gets notified, hey, this is ready, and it will then go back to the ready state, right? It's no longer blocked. It's ready to run again, but it's not. It needs to be while it was in the blocked state, the scheduler moved it off the processor it was on, put something else there instead, and so now it has to wait until a processor is ready again. So the scheduler will then, once it finds it, move it from ready to running. It will continue its processing, and this cycle between running, blocked, and ready will continue until the computation is complete, right? And at that point, it will then shift to the state dead, right? It's done, it's no longer active, and it has nothing left to do. So in that case, and what you could do is it could possibly be the task, the underlying thread that was running the task could be assigned a brand new task, but that task is done. Anyway, this leads us to the concept of liveness and deadlock. So liveness is essentially a characteristic that a program unit may or may not have, right? So in sequential code, this basically means that eventually, the unit of execution will eventually complete its execution and be done, right? So it's live until that it finishes, and when it finishes, it's dead. Well, when we're in a concurrent environment, a task can easily lose its liveness, right? It can be killed off. Maybe an error occurred, or something happened is permanently blocked. Whatever. When the problem here is that in the case that all tasks in a concurrent environment lose their liveness, it effectively no longer can process, right? If every single thing could no longer, for example, let's say that everything an error occurs because it was, there's like a timeout while it was waiting for some sort of resource, or there was just an exception occurred while processing that you weren't aware of, and all your threads die, including the main one. Well, if that happens, then your program just dies, and it could occur because of waiting around, that locking up. The worst is when, let's say we have some resource, right, a competition synchronization issue, where something is using the resource at the time, and then it dies, and then everything else was waiting for that to occur, waiting for that to unlock that resource. Well, it died in the middle of that, and so it will never unlock that, and then everything else around it dies while waiting for that to happen. And that's essentially what deadlock is. So when we're thinking about that, right, so when in order to prevent deadlock and liveness issues from happening, from causing problems, we have to really sit down and think very hard about how do we design our programs for concurrency. And so the most important things we always have to be concerned about are competition, cooperation, synchronization. If we can really, I would essentially state that if we can essentially design such that we capture correctly all the things we need when it comes to competition, cooperation, and synchronization, we can then pretty much ensure that, for the most part, on the concurrency side, our program will be correct. And then we get into issues of task scheduling, right, and how we need to make that happen. How can an application, and then how can we then use our application to influence task scheduling? And we also are in charge as the programmer of when we start and end the execution of our tasks, and finally how and when these tasks are actually created. So when we start getting into this synchronization, right, there are three major approaches that we've developed in the software in the programming world: semaphores, monitors, and message passing as our means by which we ensure that these things can occur. And so semaphores were pretty much the first main one that ever came around. And these were created by Edgar Dijkstra back in 1965. And basically what a semaphore is simply it's a data structure that consists of a counter and a queue, which then store task descriptors, right? So the counter is there. The queue stores the task descriptors, which a task descriptor is simply a data structure that stores all the relevant information about the execution state of the task, right? So is it, in running? Is it in ready? Whatever it is. Or is it blocked, waiting for something to happen? And so a semaphore can be used to implement a guard on code that accesses shared data structures. So like if we have some resource that we need to, prevent inappropriate reading, writing from happening, etc. We want to guard that so that we can control the flow of execution across that thing. We need to use something like a semaphore. And so what it really has is only two operations, right? Wait and release. And so what happens is and so then we use these to provide both competition and cooperation synchronization. Anyway, I'm going to let you guys look up more about semaphores. I'm not going to get too deep into those. Just realize that they have these operations. And basically what it says is that when something goes to execute across that, every time we have something that wants to execute the code or use the thing that's being guarded by the semaphore, what we end up saying is we then go in, we ask, can we release? If the counter is not 0, we then have to go in and say no, and we tell them that they have to wait, right? So then we say we'll wait. That puts that task into the buffer, right? Into the queue of waiting, right? And it increments the counter. And essentially, I think what actually it gives you is it gives you a value for that that counter, so that you can essentially so that when it reaches that same level, you can then use it, right? When you get to a certain level, you can use that value, and then it continues to update that counter as tasks enter and leave, right? And every time you release, you decrement the counter, so then the next one can then use it, and it continues that along the way until, and then when it's at 0, you can just go and automatically use it, and then you increment the counter as you need to. So there are some issues with this. I will leave you guys to go look that up in your spare time. I'm not really too worried about that. Semaphores have certain issues, right? Misuse of these can cause significant failures, specifically with cooperation synchronization, because what will end up happening is the buffer will overflow if the wait of full spots is left out, right? So don't worry about that. That's in the underlying components of this. I'm not going to get into that. I would suggest you go and spend some time reading about this. And furthermore, they can also cause problems with competition synchronization, in that the program will deadlock if you forgot to release your if you forget to release when you are done, right? So you have to remember to call release when you're finished with the resource. Otherwise, if that thread dies during that processing, or is gone but didn't notify everyone, then what will end up happening is all the other threads that are waiting will die while waiting. Now, monitors are a newer construct, and basically they're essentially a lock. They monitor access to a block of code, and they've been implemented in Java, Ada, and C#, along with some other languages. And the basic idea is we're going to encapsulate a shared data and its underlying operations in order to restrict access, right? So it locks a section of code from being used, right? And all this really is just some abstract data type for that shared data. And so when we use this in competition synchronization, basically what we're going to do is the shared data becomes resident within the monitor rather than in the client units, right? The client units have to come in and ask the monitor for access to the data rather than having the data inside themselves, right? And so all access resident, and then furthermore, not only is the shared data stored within the monitor, but the actual access to that data is resident within the monitor itself, right? The access being through methods, right? And so what we then do, the goal of the monitor is then to the monitor implementation is to guarantee synchronized access by allowing only one thing in at a time, right? So if I need to read or write, I lock up that piece of data until either one of those operations is done, right? So if I go to read, then you can't write while I'm reading it. And when you go to write it, I can't read until the write is done. So essentially, the calls to monitor procedures are implicitly queued if the monitor is busy. So if I go to, for example, if I'm in the middle, if one task A is in the middle of writing to our data, and task B at that exact moment in time attempts to read, task B will be queued during that period of time, and will not be allowed to read until after that write has finished. And at that time, it'll exit the queue and then go and utilize the procedure it wanted to and continue on. So if we think about this, right, these monitors provide us this capability for synchronization, for specifically for cooperation, right? Let's think about this. We have multiple processes. We have 4 different processes, and 2 of them need access to some buffer, right? So if we think about this as process 1 and process 3, right, both want to insert and remove, right? So we can think of this as they want to be able to, we don't want process 1 or process 3 to either insert or remove from the buffer at the exact same time. So process 1 can then go can insert, or process 3 can insert, but only one at a time. And then the monitor is the one who's locking that. If you call the insert, that is basically saying that we're going to push stuff into the buffer, and then remove takes stuff out of the buffer. But we only allow one in at a time. It handles its whatever it needs to do, and then when it leaves, the next one can come in. But we only allow either one of these operations, insert or remove, to happen at any one time, and we only allow one item to use the monitor at any one time. And so in Java and other languages like it, a monitor can be just a class, and it's the monitor of its internal data, and its access is through its public methods, which we have some sort of way of calling synchronized. So evaluation of monitors, right? Monitors are a better way to provide competition synchronization than semaphores. And the interesting thing about this is that we can actually use semaphores themselves to implement monitors, and we can also use monitors to implement semaphores. So you can gain either one from them, from the other one. Furthermore, support for cooperation synchronization is very similar as it was with semaphores, so it has the same sort of problems. Mainly in that we can overflow our actual buffers and things like that, so you have all sorts of issues. I would implore you to learn more about monitors. I'm not going to ask you too much about this on the exam, I don't think. Mainly, I would ask you some questions about the different types of task issues and things like that. Message passing is a general model for concurrency. It can model both semaphores and monitors. And it's not just for competition synchronization. It can actually be used for cooperation synchronization as well. So the central idea is that task communication is like seeing a doctor most of the time. She waits for you or you wait for her. But when you're both ready, you can get together or rendezvous as we could. So we think about this, right? The concept of the message passing rendezvous is that we want to support concurrent tasks message passing. In order to do this, a language would need a mechanism to allow tasks to indicate when it is willing to accept messages, and a way to remember who is waiting for its message accepted, to have its message accepted, and some fair way of choosing the next message. Note fair is in quotes. There's no real fair way to do it, but the goal is to ensure that nothing deadlocks, right? We want to ensure both that all things can stay alive, and at the same time, we don't starve out any one process that's been waiting forever. So that's what fairness is kind of going to break into. And so when a sender's task message is accepted by a receiver's task, the actual message transmission is called the rendezvous. So we think about it like this, right? So we have some task example. So we have this accept message, right? So we're going to wait. The task is going to wait at accept, right? It's going to send the message to the sender is going to send the message. When the task gets into accept, right? That's when the rendezvous occurred, right? Everything kind of worked out together, and then the task is going to go back to waiting at accept, and the sender is going to continue its normal execution. And you can just kind of see over time that in the second one, right, we have the sender waits for the task example. The first one is the task waits for the sender, and the second one is the sender waits for the task, right? So we have the task is kind of going along, it's busy, and it has the accept, right, is occurred, right? So the sender sends the message and is suspended until the accept occurs. in which place the rendezvous occurs at the sender, and then when the rendezvous is over, the sender continues its execution while the task shifts into waiting at accept. Okay, so pretty easy to understand how these rendezvous work. Well, what we can basically think of as a task has an accept clause and no other code is called, actually, I think I'm going to kind of move on. Don't worry about that. Don't worry about that part. Don't worry about that. So if we want to think about this, if we're just going to think about this as a graphical representation, if we have two tasks, task A and task B, right? Task A has some accept clauses, job 1 and job 2, and task B has some accept clauses, which are job 3 and job 4, and then you have the internal task body, right? The actual stuff going on in here, essentially our data. And so we can then, inside of task A, right, task A's going to call on B. It's going to call the job 3 method with some value, right? And that comes in, and if it accepts, if there's no one else waiting on job 3, then it will immediately accept, and that's when the rendezvous occurs. On the other hand, if there is something waiting, then task A will go into wait on accept, and then it will wait until there's an opening for it, and it will go in and to job 3, and task B will process the value that was provided to it from task A. Okay, so this is, I would sort of say that essentially the Java system is more like a message passing with monitors. But anyway, so in Java, our tasks are called threads. And what they are is they're concurrent units where we have this base class called thread, right? And what we can do is we can extend thread, and thread has a bunch of different methods like start, stop, yield, wait, sleep, notify. Well, actually, notify is from object, but anyway, it has a whole bunch of different methods. But the one that we want to override is the method run. And so this is where we will put our executing logic. And then what we can do is we can then create our new thread by saying thread myth equals new my thread, and then we call start on the thread. So we explicitly invoke that thread, right? And then it will go off and it runs in its own thread of control outside of our main thread where we did this from, or whatever thread we did this from. Well, there's a problem with this in that this is considered pretty much the worst way to do this by the current architect of the Java software system, right? He wrote a book called Java Concurrency in Practice. It's the 2 Trains book back in early 2000s. And it's pretty much the Bible for writing concurrent code in Java still today. Any other book that's on concurrent programming in the JVM uses that as its reference manual. So bear that in mind. Now, when we want to control our thread's execution, the thread class has several other methods that allow us to do this, right? We can call the yield method, which allows which is a request from our running thread to voluntarily surrender its use of the processor, and it will yield to any other waiting threads. Now note, if there are no other waiting threads, it will discontinue operating. Now we can also call sleep, and sleep just blocks the current thread for a certain period of time. And finally, we can call the join method, which is then used to force is used to force a method to block, right? The current basically is saying that the current thread will block until another thread has completed its execution. So we say join, and we give it the thread that we want to join to our current one, and so we wait until that one is done. And this actually allows us to create and control processing in a elaborate way, but an elegant way to allow us to wait for all of the threads that we started to come to an end before we finish our execution, such that we ensure that all processing is done. So threads can have different priorities in execution, right? The default is the same as the main thread, which is the norm priority. But sometimes we need to, we have some threads that we want to have a higher priority than others, and we can use max priority, and some that we want to have lower priority. For example, like the garbage collector has the min priority. It kind of just runs off in the background and may or may not get to things. Note that if you make some threads max priority and other threads min priority, you can actually reach a state called live lock or starvation, where you have a bunch of low threads that are waiting for something to happen, and in that area, the thing that they're waiting for gets blocked by something that is blocking the main thread, right? And everything's alive and waiting, but nothing is happening because you're blocked by some external force, like another process is using that resource that you can no longer access. So bear that in mind. Furthermore, you can have one thread that has such a low priority versus everything else that it never executes, and that's called starvation. In Java, we provide competition synchronization of our threads with the synchronized keyword. And what this does is it says disallows any other method from running on the object while it is in execution, right? So if we have a synchronized method, we can't call any other methods on that from other threads or from even that thread until that method is done executing. And that can actually, so if you have two synchronized methods trying to call each other from two different threads, we can actually, that's another way of causing live lock, right? We have two threads from synchronized methods trying to call the other method and thus blocking each other. That's a dangerous problem, so bear that in mind as well. Methods are not the only thing that can be synchronized. We can also synchronize in a single statement or a block of code by creating a synchronized and then curly braces block. And then in parentheses, so typically an item that's synchronized locks on the current object instance that it exists in. If you want to use a different object for the lock, right, so that controls that block of code, then you have to provide an expression that evaluates that object for that lock. So just keep that in mind. I'm not going to show you how to do that exactly. I would suggest that you go and investigate how to do that in your spare time. Cooperation synchronization for threads is provided through the built-in methods that come from objects, which are wait, notify, and notify all. And so wait tells us that what we'll do is we have to do this within a loop if we're going to do it. But what it allows us to do is it says we'll wait for a certain amount of time for everything else to occur, right? So it will allow other things to other threads to execute while we wait. We also have the notify, which says I will notify other threads that the event that they are expecting to happen has happened. And finally, we can say notify all, and that will just notify all other processors, all their methods that they should be awoken, and that they can. We're notifying them that if they are waiting on this object, they can execute now, and so then they can fight for access. So we have to note here at the time of the writing for this that the support for concurrency was relatively simple. It was back in before Java 5, back in 2000 and I think 2005, about the time that Brian Goetz was writing Java concurrency in practice. Edsger Dijkstra came out with a paper slamming Sun Microsystems and their implementation of concurrency in Java because it was extremely weak. It was not provable at all. There was serious allegations leveled at Sun Microsystems. So they sat down, completely redid all of it, and they provided not only thread and runnable as they always had, but they added in synchronized. That didn't exist until Java 4, 1.4, Java 5. They made a stronger case for the use of the keyword volatile for values. I'm not going to get into what that means. You can learn about that in your spare time. They also did a significant amount of work to develop concurrent in Java 6. Brian Goetz' concurrent versions of the collections API was developed, because do not use, if you have a concurrent system, do not use the basic built-in collections frameworks like list, array list, queue, set, map, all those different things. They are not thread safe, and you will have all sorts of issues if you have reading and writing going on with multiple threads. It will be wrong. It will cause errors that you would not expect it to cause. It's quite interesting to watch, but use the built-in ones that are there in the concurrent. Furthermore, if you need to manipulate numbers, they have atomic, the java.util.concurrent.atomic library, which gives you API, which gives you all sorts of different ways to handle numbers and other different components in an atomic way. So you can actually do that effectively and control proper reading and writing. Anyway, so bear that in mind. Those things do exist. And I think, this is a summary. So we did talk about this. So concurrent execution can be at the instruction, statement, or subprogram level. Physical concurrency what is basically the concept of when we have multiple processors used to execute concurrent units versus logical concurrency where we have concurrent concurrent units are executed on a single processor. So the difference is physical gives us actual, we have more than one processor, whereas logical is still concurrency but at a but more at a logic level rather than at a actual processor level. The two primary facilities support subprogram concurrency are competition and cooperation synchronization. The mechanisms for that are semaphores, monitors, rendezvous, and threads. And then finally, we have, don't worry about the high performance Fortran. There's all sorts of different things. We don't care about that. Java thread evaluation is in essence, oh, sorry, I went the wrong way. Anyway, so that's the end of that. And I'm going to, in a minute here, in the next part of this,